So yeah, hi everyone. My name is Jinyang Shen. I'm a first year computer science PhD student at Iowa State University, and I'll present our work, data race satisfiability on array elements. So as we all know, data race happens when two or more threads access the same memory location concurrently without proper synchronization, and at least one access needs to be erased. In case of scalar variables appearing within a OpenMP parallel for loop, this can be quite easy to see that there's a data race on that scalar variable because we know that each thread will work on that same memory location which corresponds to the variable that you're concerned with. In case of array data types, this can become relatively trickier than the scalar variables because we need to check whether the indices of the right matches with the indices of a different right or a indices of a read. This might not be a good motivating example because we can see that there's a loop query dependence, but assuming that we just want to check whether there's a data race or not in this code, we might want to just trace out how the OpenMP parallel for will execute. So for example, if we assume we have two threads and thread 0 works on I at 8 and thread 1 works on I at 9 concurrently, then we can see that there's a data race at a 9, 0. And the relation between array indexing with the induction variables along with OpenMP's work sharing model actually makes it easy to compute for whether there's a data race or not of these types using constraint solvers. This slide will share some preliminary results of data race detection using constraint solving for those data types, for array data types. So before I dive into our methodology, of course, there are existing static analysis tools that can do the same thing. There's LLOB that uses polyhedral model with LVM alias analysis. So it will first try to use the polyhedral model for affine loops to check for a data race. If the parallel for loop is not affine, then it will resort to LVM alias analysis to detect the data races. And there's also OpenRace that uses procedural analysis. So they will do pre-processing, pointer analysis, function summarization, and all the way up to happens before analysis on the LVMIR to check whether there's a data race or not. There's also a hybrid mechanism that uses that combines constraint solving with symbolic execution called PathG. In their work, they use constraint solving to first check whether there's a possibility for a data race, whether there's a possibility for a data race to happen in a parallel for loop, and they use symbolic execution to find a trace that leads to that data race. And our work is based on the constraint solving method that you have all proposed. And going back to the two static analysis tools that I mentioned, they have a problem where if they are presented with edge cases, then they can produce false positives. So for LLOB, it reports DRB54 from data race bench as having a data race, even though it doesn't have a data race here. I haven't dived deep into the implementation of LLOB to see why this is happening, but there are two possibilities. Either it's because LLOB only always used the for loop that is marked with parallel for. So it might be the case that it has no knowledge of the outer loop, or there might be a bug in the implementation where it triggers alias analysis instead of polyhedral model analysis. So those are two possibilities why it can trigger a false positive. And for OpenRace actually does not consider control paths to avoid path explosion problem. So in the case of the code that produces data race being in that code region, then it can trigger a false positive and report that as having a data race. And another motivation for this work is that using constraint solving, we could avoid these types of false positive detections. So I'll just quickly show you how an OpenMP parallel for loop can be modeled as a set of constraints. So assuming that we have the code that you see on the left-hand side, the corresponding thread model is somewhat similar to what you would see on the right-hand side, although it's not really that accurate. But assuming that we have two threads, thread 0 working on I at 4 and thread 1 working on I at 14, then we can see that there's a dependence on ARR 28, and there's a data race for that. And so to model this as a constraint, you et al. In their work, they propose different variations of the constraints. They have the variation where they check for which thread ID works on which chunk of the loop. There's also another variation for accounting for dynamic scheduling with explicit chunk size. And the last one, in this case, we assume the maximally pessimistic view, where we assume that we have the number of threads we have is equal to the number of iterations the for loop is going to have. So in this case, we have 0 to 14 iteration, and we will have thread ID from 0 to 14. But if we actually assume that maximally pessimistic view, we do not need all 15 threads. We just need to create 2 logical threads where their induction variable values differ. So that's why in the first row, we have the requirement that says we're creating 2 logical threads and their corresponding induction variable values should differ. And in the second row, we add the constraint for the boundaries of the induction variables. And in the last row, we add a requirement to check whether the index of the right can match with the index of the read. And we send this to a constraint solver, and that can tell us whether if the constraint solver can find a solution for it, then it will report this as having a data race. If not, it will not report it as having a data race. And we've seen that there can be a data race at ARR 28. So what we contribute in this work is that we provide an implementation for the constraint solving proposed by you et al. In their original work, although they explain it pretty well, they do not actually provide an implementation for it. So we provide an implementation adhering, it doesn't really strictly adhere to the constraints provided by you et al, but it's mostly similar to see the viability of constraint solving for data race detection. And we also do an evaluation on the subset of data race bench. In the original work, they do not use data race bench. They used, I believe, files from the OpenMP website. And in case if you're wondering why it's a subset, this work is relatively incomplete in the sense that it doesn't really support all the constructs and directives in OpenMP. So we have to use a subset of the race bench. And I wouldn't say this is a contribution, but the way we do differently is that in the original work, we use symbolic execution, not only for finding the trace of the data race, but they also use symbolic execution on a version of the C code. So code without OpenMP premise to get the values of the variable that might be used in and that can help with solving the constraints. But in our work, without doing small execution, although limited, we try to determine those statically. So before we get into the implementation, I'll just show you how a constraint solving can avoid the false positives presented. So this is DRV 54, and we can see that the inner loop is parallelized, but the outer loop isn't. So that's why we have J0 and J1 that corresponds to the predicate copies of the induction variables of the inner for loop. And in the second row, we provide the constraint for the induction variable of the outer loop. And like I mentioned, it's not parallelized, so we only provide one variable for that. And in the third row, we provide the boundaries of the induction variable for J's. And in the fourth row, this is a requirement to this is a constraint to check whether the index of the right matches with the index of the read. So we require that the columns of B needs to match, and also the rows of B needs to match. And in this case, we have the I and J are bounded by N and M. And N and M's values can be determined statically, so we put a bound on those variables as well. And if we send this to a constraint solver, what it will realize is that, so to find a solution for it, each variable needs to be fixed. And for a fixed variable, I cannot be equal to I minus 1. So that becomes unsatisfiable, and that means no data race occurs. So I think I mentioned this, but if there's a solution for this constraint, then there is a data race. If it cannot be satisfied, then there is no data race. There can be a third case where the constraint solver tries to find a solution indefinitely, but I think at least the ones that I use, they have bounded search depth, and that results in I believe no solution found. And so we can generally assume that it's either a data race or no data race. And in case of dead code region, the constraint solver in this case can find that the predicate of this if statement will not get satisfied, and that will also report that there is no data race there. So in terms to construct the constraints, we use G proposed by Marsden et al. In their work OpenMP Dart. As the name implies, it just combines AST with the edges from the control flow graph. And so, for example, if we have a code that you see on the right-hand side, the corresponding AST CFG would look something like you would see on the left-hand side. And so we actually require the user to put a custom parameter to tell us what for loop that you want to analyze. So in this case, we know what for loop we want to parallelize. So we want to parallelize this for loop, and so we create two private copies of the induction variables and we put the bounds for those induction variables as well. And once we go down the AST CFG, we encounter a write operation and a read operation, and we add that to the overall constraint as well. Like I mentioned last time, the last constraint is checking whether the index of the write can match with the index of the read. And obviously there's an if statement there. That's the condition for read and write to happen. So we put that into the overall constraint as well. And we send this to the constraint solver, and the constraint solver will realize that once I0 and I1's values are fixed to be 20, this solution cannot be satisfied and no data race is reported. So in terms of implementation at a higher level, what we do is we do multiple passes on the AST CFG. So in the first pass, we gather the values of the variables. Due to its limitations, we only collect the integer variable values at this moment. And in the second pass, we encode loop bounds. So what are the boundaries for the induction variables? And in the third pass, we encode array dimensions and the expressions used for indexing the array. And at the same time, we construct a read set and a write set. And using those information, we construct formulas that check for write after write and read after write. We do not check for write after read, even though we can, because it would be just how we combine the elements from the read set and write set. We do that to save time, and generally read after write is equivalent to write after read in a parallel for loop. So we only check for those two. And after constructing the constraints, we use the Z3 SMT solver to solve for constraints, and that can tell us whether there's a data race or there is no data race. So for the evaluations, doesn't really tell much because we use the subset of data race bench. Like I mentioned, we have to exclude the files that do not meet the criteria or the files that are not supported. The last row represents our work. And what this shortly tells us is that although we were able to avoid false positives, we actually ended up with more false negatives. This is because we're actually doing a case-by-case analysis on the AST CFG pattern. So if the detection algorithm expects some certain pattern that it wants to see, but if the actual code does not fit into the pattern, what ends up happening is it ends up creating a malformed SMT formula, which surprisingly it's syntactically correct, but the semantics of the for loop is encoded wrongly, so that results in producing more false negatives. Oh, and for OpenRace did not report any false positives out of the 55 files, but like we've seen from previous slides, in the case of dev code, it can report that as having a data race. So that brings us to the limitations. Like I mentioned, the constraints are not yet generalized, and we're doing a case-by-case analysis on the AST CFG. So actually, most of the development time just went on debugging the edge cases rather than focusing on supporting various constructs. And the user needs to put a custom pragma for analysis. And fortunately, we're only allowing one analysis at a time. Although we can just remove that constraint. The reasoning behind this was the constraints are not optimized. So essentially, we can think of it as we're just throwing in a bunch of constraints to the SMT solver, and that could lead to heavy performance. So we're putting in only one pragma analysis for at a time, but we can always remove that. And there's limited support for retrieving the intermediate values of the variables. So like I mentioned, in the original work, they use symbolic execution to get the values of the variables. So for example, we've seen from DRV54, we bounded the values for n and m. And we were able to do that because we could determine those statically. In case of, in the original work, they will use symbolic execution to check that values. And so the future work, I think we would have to eventually port this to LLVM-IR rather than doing this at the AST level, because doing this at the AST level, I believe it's not scalable. And instead of tackling each edge cases on the AST, we can just replace that part with the pre-built passes that the LLVM has. And by doing on supporting multiple constructs and directives rather than focusing on tackling the edge cases. And we're also looking into adopting hybrid modular techniques for determining the values of the variables. So like I mentioned again, original work uses symbolic execution, but symbolic execution on a sequentialized code, especially with loops, can be expensive. So what we can maybe do is we can instrument the code and then run it dynamically to retrieve the values of the variables, or if we want to just get a quick result at the cost of lower accuracy and precision, we can maybe ask an LLM or fine-tune the LLM to retrieve those values of the variables. But if anything novel comes up, then we can just switch to that novel idea that can come in the future. And so takeaway is that adding more constraints that encode program context can help with elimination of the false positives, but without generalized method and extensive support, false negatives and other weird anomalies can also arise, and that can defeat the purpose of data race detection. And yeah, that would be it for me. Thank you.
Any questions?
Hi, how fast or slow is your approach compared to LLOP and OpenMP?
I did not measure that, but to give you a hunch, it's actually slower because so the AST traversal is done with client front end, and the formula creation and actually solving for the constraint, we use Python for it. So the overall execution would be actually slower.
Is the Z3 solving like the slowest part, or is it the front-end analysis?
The Z3 solving.
Z3.
Any other questions in the room?
So you said that the AST creating constraints based on the AST in scale, and you proposed to anything to the IR. But I was wondering why do you think that is? What is it about AST that can scale?
Oh, so are you saying that AST will scale?
Yeah, no, you said that it wouldn't. I was wondering why you said that.
Because if we want to do this at the AST level, at least as far as I know, there's no constraint or developing the constraint at the AST level. So actually not in terms of scalability, but in terms of development, LLVM-IR, I think it would be better because we can just use passes that LLVM has rather than just tackling the edge cases of the traversal.
Any more questions? Let's check before. No. Okay, one question. You mentioned that this is based off a previous work. Can you just briefly talk about the key differences between your implementation and their proposed work?
Yeah, so in their work, they actually have 3 variations of the constraint solving. They have one for static scheduling and one for dynamic scheduling and one for maximally pessimistic view, which is what we take. But I had a meeting, I think, about 1.5 years ago with Dr. Dorfert from LLML, and he said that thread sensitive data reads should be treated as data reads. At least in his experience, he said he hasn't seen any weird manipulation of the thread chunks to avoid data reads. If that makes sense, but I took that advice and then I just assumed the worst case possible, and they use symbolic execution to put the bounds on the variables, whereas we try to determine that statically. So there's only a minimal difference. Yeah.
Okay, I can see that. If the same thread is doing the two iterations, then it would not be a race because it will go sequentially down. There are no more questions. Let's thank our speaker again.